We are back, and this time we shall be discussing the dynamics of first order system. We have already modeled first order system, and in first order system we had modeled the first order lag system as well as the first order pure capacitive process. So dynamics means how the things change with time, how the things behave given any kind of input. We can give a sinusoidal input, we can give an impulse input, or most of the cases, as in this time as well, we shall be giving a step change. And normally, to start with, we give a unit step change. Unit step change means that the magnitude of step is 1 at t is equal to 0. It's given, so all times t equal to or less than 0, the value is 0, and all times t greater than 0, the value is unity. So that is called unit step change. That's the forcing function that we give, and we will see if this step change is given to the first order system, again, which are of two types. We will start with the pure capacitive type and see how the output changes with respect to time. So that is what we know as dynamics of first order system. In this case, to start with a pure capacitive process. So as you know, as you can see on the screen, which I will highlight with the pointer as well, that if it is a pure capacitive process, we have already seen the transfer function of a pure capacitive process. It happens to be this GS is in terms of deviation variables, deviation variable of the output divided by deviation variable of the forcing function, whatsoever we will be in this case. That transfer function is given by k dash p divided by s, and k dash p is the gain of the system. So we have to give the value of fs, and fs for unit step function, it's the Laplace transform of unit step function, we all know, is given by 1 by s. And that's what we are going to see, that for all values of t greater than 0, the value of ft, unit step change, is 1, and the Laplace transform for this unit step change is given by 1 by s. So this fs is going to come over here, and this is nothing but 1 upon s. So ultimately the output will become k dash p divided by s square. So that's what it's going to be, and let's see. This ys is going to be, as I said, k dash p upon s square. So if we take the Laplace inverse of this k dash p upon s square, 1 upon s square, the Laplace inverse of that is t, simply t. So it will get multiplied by t. So as we see that, as I have already told you, that y dash t is equal to k dash p into t. Now this k dash p is constant. It is constant. It's a gain of the system, the first order pure capacitive system. It means that the output will continue to rise with t. T means straight. T is equal to 0, output is equal to 0, t is equal to 1. Output will be equal to k dash p, t is equal to 2, output will be equal to 2 k dash p, at t is equal to 3, it will be 3 k dash p. It's going to straight change linearly with time, and its slope will be given by k dash p. It's a straight line with the slope k dash p. That's what we can imagine its output graph to be as it changes with time. Let's see what's there in the next slide. Yes, this is what it is, that the output is going to change with respect to time linearly with the slope. This is the slope tan of theta that is given by k dash p. So what we see is that this kind of system is going to go on and on and on and on and on and on and on. It's an unbounded thing, unbounded. It's not going to contain itself, and at t is equal to infinity, this output will also be infinite. It means that this is an unbounded output. So this is the unbounded response of a pure capacitive process. It's not going to regulate. It's not going to at any stage become saturated at this time or come down at some stage. It's going to go on and on and on. So it is not self-regulated. It is not self-regulated. So we say its response is in the form that it's a pure integrator, it's a pure integrator, it's a pure capacitive. In this case, this is the relationship between the input and the output. Once again, because it's an unregulated one, so pure capacitive processes can cause serious control problems because they cannot balance themselves. That's why you have to be very, very cautious. Wherever you have a pure capacitive process, we have to be very cautious to put some external agency, some external mechanism to contain. Otherwise, it will go on and on and on and break all the boundaries. This is not what we want. Once again, for the final time, it's highlighted that this attribute is known as non-self-regulation, because we will see in the subsequent slides that this is only with the pure capacitive that it's non-self-regulatory. Otherwise, in most of the cases, the regulation takes place by itself. Let us see how is it going to happen in the next slide. Coming to the dynamic response of the first order lag system. If you remember first order lag system, the transfer function of that was given by Kp divided by tau p s plus 1. Tau p is the time constant, Kp is the gain, y is the output in terms of deviation variable. I'm again and again telling so that there be no confusion and you need to be reminded. And similarly, the deviation is from the steady state, and this is the forcing function again in terms of deviation, and again it's deviation from the steady state, and we are going to give the step change as we did earlier. So giving the step change, which is given by 1 by s. So this entire thing means this entire thing is getting multiplied by 1 by s. So once it's multiplied by 1 by s, this s comes in the denominator. And if we take the partial fractions of this can be broken into kp by s minus kp tp divided by tau p s plus 1. It's tau p. So if you're not very sure, you can just take the LCM and cross multiply and see we do get the same thing or not. So this is the partial fraction, breaking this into this, and then we're going to take the Laplace inverse. Laplace inverse of this will be simply Kp, and Laplace of inverse of this will be something in the form of delay, and that delay is going to be in terms of tau p. So let's see if we get it. What do we get in terms of t? So taking this kp out, taking this kp out, so what do we get over here is it's something which you have been doing right from if not first semester, then maybe from second semester onwards, taking the Laplace ever since you were given exposure to Laplace, or even charging and discharging of LR circuits and CR circuits and so on and so forth. They all yielded this result only ultimately. So this is the outcome of the first order system, where we have Kp as the gain and tau p as the time constant. So that's how it's going to change with respect to time. It's exponential charge build up exponentially over there. It's going to saturate at 1, because if you see, if I put t is equal to infinity, then this entire thing will become 0, and I will get this yt will be equal to kp. So, or if I divide the yt by kp, that's I'm normalized, then yt upon kp at t is equal to infinity will be unity. This is what we get. It's going to contain itself at 1. It's not going to become infinity. Say in case of pure capacitive systems, at t is equal to infinity, the output was becoming equal to infinity, and that's why we said it's a non-regulating kind of system. But in this case, at t is equal to infinity, it's going to saturate itself at kp, or in this case you can say if it's a normalized one, then at 1, if we take yt upon kp, then it's going to saturate itself at 1. So that's why this, unlike the pure capacitive systems, is a regulated system, a regulated, self-regulated system. Let us see. Now, instead of taking the forcing function as 1 upon s. Instead of this 1, if I take it as a, where a is the magnitude, then the same a will come over here, the same a will come over here, and here the same a will come over here. It means that if it is at with the magnitude a, then the output will also get, the entire thing will get multiplied by a. So this is something which is quite obvious, but normally we do not give the step change of magnitude a. Normally we get of step change of unit only, but even if we give so a, this a is going to get multiplied in the result as such. So there should be no doubt or no ambiguity on this. Now this, as you see, is it's very clearly mentioned that it's a dimensionless response of the first order lag. It's a first order lag, it's not pure capacitive, to a step input. Why it is called dimensionless? Because along the x-axis what you are getting is yt upon a into kp. A is magnitude of the step and kp is the gain, and this yt upon kp is going to saturate at 1. This is what I've been telling you again and again, and this time is not in terms of tau, but it's in terms of tau upon tau p. Once it's a tau upon tau p, it's coming out to be 1 2 3 4. It's always the same irrespective of whatsoever may be the process. So if at all you change the process, what you can change in process is you can change the kp. What else you can change in process is you can change its time period. What else you can change in the forcing function is a. There is not any other thing other than these three things which can be changed, and if you divide this by this and this by this, you will get a response which is universal. Universal means irrespective of whatsoever may be value of a, whatsoever may be value of kp, whatsoever may be value of tau p, it's going to be like this. It's going to saturate at 1 every time. And you see the slope. If you continue with the same slope as it was at t is equal to 0, it's going to reach the final value in 1 tau p. This is 1 tau p, this is 2 tau p, because it's t upon tau p is equal to 2. It means t is equal to 2 tau p. At 2 tau p, as you see over here, that at 0 the value is 0. At 1 tau p, if you continue over here, it's going to reach over here at 1 tau p. But if you move along the curve, then you see at t upon tau p is equal to 1, that is t is equal to 1 tau p, this will be something like 63.5 or something like that, 63.5% over here. And then if you continue to move, and what will happen at t upon tau p is equal to 2, that is at t is equal to 2 tau p, this will be approximately 85%. And at t is equal to 3 tau p, that is t upon tau p is equal to 3, this will be something like, you can say, 95%. And at t is equal to 4 tau p, this is 98%. So once it reaches 98%, we say it is almost the final value. 98% and 100%, this 2% settling value anyways is there. So we will not even go for what it's going to be like at t is equal to 5 tau p and 6 tau p. We can be very sure, and so we can be content with that. In the first order systems, after 4 tau p, we say the things are fairly as near to the steady state as finally going to be. So 98% of the steady state is good enough in most of the cases. So this is the dimensionless response of the first order lag to a step input change, which is universal, irrespective of the gain, irrespective of the time constant, irrespective of the magnitude of the step input as we have taken over here. The things which we want to conclude from this is, the first one is that the process is self-regulating, because at t is equal to infinity, the output is not becoming infinity, it's regulating itself to certain value, and in dimensionless form it's regulating to unity. This is the first and the foremost thing which is distinguishable from the other one which we had taken, which was a pure capacitive system. The first order lag processes are self-regulating. Second thing, that the slope of this curve at t is equal to 0, if you continue to move at that rate, then it will in first time constant itself at tau is equal to tau p, you will get the output will become equal to 1. This implies, I'm reading it verbatim so that it's very clear to you all, that if the initial rate of change of yt were to be maintained, the response would reach its final value in one time constant, that means in 1 tau p. Obviously, smaller the value of time constant, steeper will be the initial response of the system, faster will it reach the final value. And this time constant tau p of a process is a measure of the time necessary for the process to adjust its change to its input. Again, 63% in first tau p, 85% in the second tau p, 95% in the third tau p, and almost final value 98% in the fourth tau p. Uske baad we don't care much. What is tabulated over here? 63.2% and 86.5%. These are the approximate figures I've given you in first tau p, second tau p, third tau p, and fourth tau p. Finally, if we take note of the kp, the gain, what's the meaning of gain? Gain means that if gain is large, it means you have to give a small change in input to get good amount of change in the output. But if kp is small, gain is small, then we have to give good amount of input even if you want to bring about the same amount of change in the output. So this is the significance of kp and significance of tau. So this is what we're going to compare the two systems with same gain but different time constants, and then the same time constant and different gains. What's the effect of the gain and what's the effect of the time constant? That's what we are going to see in the next slide. So friends, this is the last, and here we go, that you have two tanks with the same gain. One tank has more area, one tank has lesser area. You can say that A1 is more than A2. So A1 is a bigger tank and A2 is a smaller tank. So obviously you give any change in the step input in the flow rate, then it's going to change its level. The bigger tank will take more time to fill and the smaller tank will take lesser time to fill. It will quickly fill, but both will fill to the same level. As such, we see over here, and this is the time constant. This is a time constant because area of cross section is given as the time constant. This is what we have proved earlier also. What if the time constants are the same? What if the time constants are same but the gains are different? So the one with the lesser gain, the final value of that will be smaller. One with a greater gain, the final value of the tank will be the level will be higher. So the gain is given by R1 and R2 over here, and obviously we have seen that as we have seen that the gain was lower, R1 is less than R2, the gain was lower, so it saturated earlier. Gain was higher, it saturated in a higher manner at a higher level. So this is the effect of gain. This is the effect of gain on the response, on the dynamic response, and this is the effect of time constant on the dynamic response of the first order lag system. So this is the effect of time constant, as you can see over here, and this is the effect of static gain. In this case, kp2 is more than kp1. So friends, this was about the dynamics of first order system as we have seen in this session. So in case you have any queries or doubts, or you want to share some of your experiences, practical or theoretical or whatsoever you feel, you can contact me through WhatsApp or through Zoom or through the cell phones. You can make a phone call over there, and you can always have face-to-face interaction if allowed. So I hope you have enjoyed this session, and more things might be coming to your mind after attending this session. This was the first order system. The next thing which comes to your mind, that okay, this was first order system, so will we be going in for second order, third order, fourth order also, and how complicated or how interesting or how head scratching will those be? I hope you can always make some proactive steps and read ahead of me also, so that you can better receive the instructions in the next session. I hope you all will be participating in a manner that's going to make this all the more interesting. I thank you for being with me, and I wish you a very safe stay. Bye bye.